Schottky diode.
The Schottky diode, also known as hot carrier diode, is a semiconductor diode with a low forward voltage drop and a very fast switching action. The cat's whisker detectors used in the early days of wireless and metal rectifiers used in early power applications can be considered primitive Schottky diodes. When current flows through a diode, there is a small voltage drop across the diode terminals. A normal silicon diode has a voltage drop between 0.6–1.7 volts, while a Schottky diode voltage drop is between approximately 0.15–0.45 volts. This lower voltage drop can provide higher switching speed and better system efficiency.
Construction.
A metal semiconductor junction is formed between a metal and a semiconductor, creating a Schottky barrier instead of a semiconductor. Semiconductor junction as in conventional diodes. Typical metals used are molybdenum, platinum, chromium or tungsten, and certain silicides, for example palladium silicide and platinum silicide. And the semiconductor would typically be N-type silicon. The metal side acts as the anode and N-type semiconductor acts as the cathode of the diode. This Schottky barrier results in both very fast switching and low forward voltage drop. The choice of the combination of the metal and semiconductor determines the forward voltage of the diode. Both N and P-type semiconductors show the Schottky effect. The P-type has typically much lower forward voltage. As the reverse leakage current increases dramatically with lowering the forward voltage, it cannot be too low. The usually employed range is about 0.5–0.7 V, and P-type semiconductors are employed only rarely. Titanium silicide and other refractory silicides, which are able to withstand the temperatures needed for source drain annealing in CMOS processes, usually have too low forward voltage to be useful. Processes using these silicides therefore usually do not offer Schottky diodes. With increased doping level of the semiconductor, the width of the depletion region drops. Below certain width, the charge carriers can tunnel through the depletion region. At very high doping levels, the junction does not behave as a rectifier anymore and becomes an ohmic contact. This can be used for simultaneous formation of ohmic contacts and diodes, as diodes form between the silicide and lightly doped N-type region and ohmic contacts form between the silicide and a heavily doped N or P-type region. Lightly doped P regions pose a problem as the resulting contact has too high resistance for a good ohmic contact and too low forward voltage and too high reverse leakage to be a good diode. As the edges of the Schottky contact are fairly sharp, high electric field gradient occurs around them which limits the reverse breakdown voltage. Various strategies are used, from guard rings to overlaps of metallization to spread out the field gradient. The guard rings consume valuable die area and are used primarily for large higher voltage diodes, while overlapping metallization is employed primarily with smaller, low voltage diodes. Schottky diodes are often used as anti-saturation clamps on transistors. Palladium silicide ones are excellent here due to their lower forward voltage, which has to be lower than the forward voltage of the base collector junction. Platinum silicide ones have forward voltage closer to that and require more attention in layout. The Schottky temperature coefficient is lower than the coefficient of the BC junction, which limits the use of PTC at higher temperatures. For power Schottky diodes, the parasitic resistances of the buried N+ layer and the epitaxial N-type layer become important. The resistance of the epitaxial layer is more important here than for a transistor, as the current has to cross its entire thickness. It however serves as a distributed ballasting resistor over the entire area of the junction and prevents localized thermal runaway under usual conditions. In comparison with the power PN diodes, the Schottky diodes are less rugged. The junction lies in direct contact to the thermally sensitive metallization. A Schottky diode can therefore dissipate less power than an equivalent size PN1 with deep buried junction, before failing, especially during reverse breakdown. The relative advantage of lower forward voltage of Schottky diodes is diminished at higher forward currents, where the voltage drop is dominated by the series resistance.
Reverse recovery time.
The most important difference between the PN and Schottky diode is reverse recovery time, when the diode switches from conducting to non-conducting state. Where in a PN diode the reverse recovery time can be in the order of hundreds of nanoseconds and less than 100 nanoseconds for fast diodes, Schottky diodes do not have a recovery time, as there is nothing to recover from, that is no charge carrier depletion region at the junction. The switching time is 100 picoseconds for the small signal diodes, and up to tens of nanoseconds for special high-capacity power diodes. With PN junction switching, there is also a reverse recovery current, which in high-power semiconductors brings increased EMI noise. With Schottky diodes, switching is essentially instant with only slight capacitive loading, which is much less of a concern. It is often said that the Schottky diode is a majority carrier semiconductor device. This means that if the semiconductor body is doped N-type, only the N-type carrier's mobile electrons play a significant role in normal operation of the device. The majority carriers are quickly injected into the conduction band of the metal contact on the other side of the diode to become free-moving electrons. Therefore no slow, random recombination of N and P-type carriers is involved, so that this diode can cease conduction faster than an ordinary PN rectifier diode. This property in turn allows a smaller device area, which also makes for a faster transition. This is another reason why Schottky diodes are useful in switch-mode power converters. The high speed of the diode means that the circuit can operate at frequencies in the range 200 kHz to 2 MHz, allowing the use of small inductors and capacitors with greater efficiency than would be possible with other diode types. Small-area Schottky diodes are the heart of RF detectors and mixers, which often operate up to 50 GHz.
Limitations.
The most evident limitations of Schottky diodes are the relatively low reverse voltage ratings for silicon metal Schottky diodes, typically 50 V and below, and a relatively high reverse leakage current. Some higher voltage designs are available. 200 V is considered a high reverse voltage. Reverse leakage current, because it increases with temperature, leads to a thermal instability issue. This often limits the useful reverse voltage to well below the actual rating. While higher reverse voltages are achievable, they would be accompanied by higher forward voltage drops, comparable to other types. Such a Schottky diode would have no advantage unless great switching speed is required.
Silicon carbide Schottky diode.
Schottky diodes constructed from silicon carbide have a much lower reverse leakage current than silicon Schottky diodes, and higher reverse voltage. As of 2011 they were available from manufacturers in variants up to 1700 V. Silicon carbide has a high thermal conductivity, and temperature has little influence on its switching and thermal characteristics. With special packaging, silicon carbide Schottky diodes can operate at junction temperatures of over 500 kelvins, about 200 degC, which allows passive or diode cooling in aerospace applications.
Applications. Voltage clamping.
While standard silicon diodes have a forward voltage drop of about 0.7 volts and germanium diodes 0.3 volts, Schottky diodes voltage drop at forward biases of around 1 mA is in the range 0.15 V to 0.46 V. See the 1N5817 and 1N5711 datasheets found online at manufacturers' websites, which makes them useful in voltage clamping applications and prevention of transistor saturation. This is due to the higher current density in the Schottky diode.
Reverse current and discharge protection.
Because of a Schottky diode's low forward voltage drop, less energy is wasted as heat, making them the most efficient choice for applications sensitive to efficiency. For instance, they are used in standalone off-grid photovoltaic PV systems to prevent batteries from discharging through the solar panels at night, called blocking diodes. In grid-connected systems with multiple strings connected in parallel, in order to prevent reverse current flowing from adjacent strings through shaded strings if the bypass diodes have failed.
Power supply.
They are also used as rectifiers in switched-mode power supplies. The low forward voltage and fast recovery time leads to increased efficiency. Schottky diodes can be used in power supply O-ring circuits and products that have both an internal battery and a mains adapter input, or similar. However, the high reverse leakage current presents a problem in this case, as any high-impedance voltage sensing circuit, for example monitoring the battery voltage or detecting whether a mains adapter is present, will see the voltage from the other power source through the diode leakage.
Designation.
Commonly encountered Schottky diodes include the 1N5817 series 1A rectifiers. Schottky metal semiconductor junctions are featured in the successors to the 7400 TTL family of logic devices, the 74s, 74LS and 74ALS series, where they are employed as clamps in parallel with the collector base junctions of the bipolar transistors to prevent their saturation, thereby greatly reducing their turn-off delays. Small signal Schottky diodes such as the 1N5711, 1N6263, 1SS106, 1SS108, and the BAT41-43, 45-49 series are widely used in high-frequency applications as detectors, mixers and nonlinear elements, and have superseded germanium diodes. They are also suitable for electrostatic discharge (ESD) protection of sensitive devices such as EV semiconductor devices, laser diodes and, to a lesser extent, exposed lines of CMOS circuitry.
Alternatives.
When less power dissipation is desired, a MOSFET and a control circuit can be used instead, in an operation mode known as active rectification. A superdiode consisting of a PN diode or Schottky diode and an operational amplifier provides an almost perfect diode characteristic due to the effect of negative feedback, although its use is restricted to frequencies the operational amplifier used can handle.